Section 2.3 is a star section. We want to find a derivative. A derivative is instantaneous rate of change. That is the slope of a tangent line. What a tangent line is a line that touches the curve at one point, let's say A. Actually, let's leave it general. Let's say at some point X. So I need to find the slope of that line, and of course this is y equal f of x. So this point right here is x f of x. The issue with that, to find a slope of a line, I need 2 points. So somebody came with the idea of, well, you know what? Take x and add a delta x to that. That makes this point x plus delta x. And the y associated with that, x plus delta x, f of x plus delta x. And they said, well, why don't you find the slope of this line? So the slope of this line would be y2 minus y1 over x2 minus x1. y2 is f of x plus delta x minus y1 is f of x over x2, which is x plus delta x minus x. The x's cancel out, so I'm getting the slope of the secant, as secant means a graph that crosses a curve at 2 points. But if I find the slope of this line, that's really the slope of the green line. You'll say, wait a minute, the slope of this line is not the same as this line. And somebody came up with the idea of, okay, instead of delta x, take half of delta x. Instead of adding delta x, add half of delta x. Find the slope of this secant line. And can you see what just happened? The slope of that line will still be this, because you're going to call this delta x, right? So the brown line is closer to the red line than the green line was. And if I were to go ahead and cut that again in half, let me pick, let's say this guy. If I cut it in half, if I find the slope of this line, I know it's a bit hard to see this color, but do you see that the slope of this line is very close to the red? Now, I had an x, let me use it back. I had an x, I added some delta x, then I cut delta x in half, then I cut delta x in half. Do you see that I'm trying to shrink this back to x? Well, if delta x was a value, then I cut it in half, the second stage. Then I cut this in half. Do you see that if this is 10, this is 5, this is 2.5? So what I'm doing, I'm shrinking delta x to 0. If delta x approaches 0, then I get the two lines infinitely close. And therefore, that would be a very good approximation of x itself, the tangent line. So this is the slope of the secant line. If I want the slope of the tangent line, all what I have to do is take the limit as delta x approaches 0 of this, and that should be the slope of the tangent line. So slope of the tangent line. So the way it works, this is the definition. This is what's known as a derivative. Derivative is the limit as delta x approaches 0 of f of x plus delta x minus f of x. And the notation Derivative is what we call it in calculus, but different fields have different names. Normally we call it f prime. It could be y prime. dy dx, that's the same thing. d dx of f, that's the same thing. In differential equations they use these notations. This is the most used. Another name for a derivative in physics, they call it velocity. And we have a main use for it. We call it the slope of the tangent line. And what that is a line crossing a curve at one point. This is also called instantaneous velocity. So slope of a tangent line is a derivative. And what's a derivative is taking f of x plus delta x minus f of x divided by delta x, which is called the difference quotient, and taking the limit as delta x approaches 0. Now, there are no examples in this section. The only examples where we use this definition is in section 2.4, and 2.4 is not required to cover, not for your class. So the idea is, if I find the slope of a tangent line that's instantaneous rate of change, or simply its velocity. And I do want to point out a normal line is perpendicular to a tangent line. That indicates the slope of the normal is -1 over the slope of a tangent, the reciprocal. And let me just demonstrate really quick how this works and why are those useful. If I have a curve y equal f of x, if I find the tangents tell me how is the curve behaving at these points. That's very useful to know. So the red would be the slope of the tangent. The slope of the normal line is perpendicular. That's also very useful. That gives me a very good idea of what the function is doing at all of these different times. So the only definition in the book that talks about a normal line, it simply says this: a normal line is perpendicular to a tangent line, which means once you find the derivative, which is the slope of the tangent, the slope of the normal line is the negative reciprocal. We're going to do a couple of examples in 2.5, and then we'll go for the rest.